Welcome to this video. And in this video, we'll be addressing the jury's stability test for discrete time systems. The jury's stability test for discrete time systems. In my previous video on stability analysis of discrete time systems, we discussed the concept of stability analysis in the Z plane. We discussed stability analysis as carried out in the Z plane. And we said that a system will be said to be stable if all the roots of its characteristic equation fall inside a circle of unity radius in the Z plane. We also carried out the stability analysis using the Raud stability criterion. And in the Raud stability criterion, we take the characteristic equation, which is a polynomial in Z, and convert this into or transform this into a polynomial in W by applying the transformation Z is equals to W plus 1 over W minus 1. Once we have the polynomial in W, we formulate the Raud array. And from the Raud array, we check for sign changes in the terms of its first column. And if there are no sign changes, we concluded that the system is said to be stable. Jury's stability test is the third method of establishing the stability of discrete time systems and is carried out as follows. Given the characteristic equation of the discrete time system as a polynomial in Z, Q of Z is given by an Z power n plus an minus 1 Z power n minus 1 plus all the way to the terms a1z plus the constant a0 is equals to 0. If this is the characteristic equation of the discrete time system, the jury's array is formulated as follows. Jury's array is formulated as follows. So we first write the order, that is the powers of Z from power 0 to power n as Z power 0, Z power 1, Z power 2, all the way to Z power n minus 2, Z power n minus 1 to Z power n. Then the terms of the first two rows of the jury's array are obtained using the coefficients of its characteristic equation as A0, A1, A2, all the way to an minus 2, an minus 1 to an. The second row, we start with an minus 2, or an minus 1, an minus 2, all the way to the terms a2, a1, a0. So the first two rows, we determine the values of the terms of the first two rows using the coefficients of its characteristic equation from a0 to an in the first row and from an to a0 in the second row. The terms of the subsequent rows are established as follows. So they will be B0, B1, B2, all the way to bn minus 2 to bn minus 1, where b0 will be the determinant of a0, an, a0. So we take the first terms of the first two rows and the last terms of the first two rows. B1 will be given by A0, AN, the terms of the first two rows, and the second last terms as AN minus 1, A1 determinant, from which then we can obtain any DK, any K term of the third row So any kth term of the third row can be obtained as A0, AN, and then AN minus K, AK determinant. The fourth row, we just reverse the terms as BN minus 1, BN minus 2, BN minus 3, all the way to B1, B0. Then the next row will be C0, C1, C2, all the way to Cn minus 2. And then the third one will be the fifth row will be the fourth row in reverse order as Cn minus 2, Cn minus 3, Cn minus 4, all the way to C0, where again C0 will be using the previous two rows, the previous two rows, the rows of the B's as B0, Bn minus 1, Bn minus 1, B0 determinant. That is the first two terms and the last two terms, you formulate their determinant. Similarly, C1 will be B0, Bn minus 1, and then Bn minus 2, B1 determinant, from which then we can tell that for any CK, the determinant will be obtained by B0, Bn minus 1, and then Bn minus 1 minus K, Bk determinant. We proceed until when we have exhausted all the terms and we'll formulate the jury's array. Once we have the jury's array, stability of the discrete time system is analyzed as follows. Condition number 1 is that Q of 1 must be greater than 0. In other words, into our polynomial in Z, where there is Z, we substitute with 1, and the value that you obtain must be greater than 1. And that is the first condition. Condition number 2 is that negative 1 power n multiplied by Q of negative 1 must also be greater than 0. So into our polynomial in Z, if we substitute for Z with negative 1 into the entire polynomial in Z, and then we multiply that with negative 1 raised to the power of n, where n is the order of the system, that should also be greater than 0. Condition number 3, which does not also depend on the jury's array, is that the magnitude of A0 must be less than the value of an. The magnitude of A0 must be less than an. In other words, in our polynomial in Z, the magnitude of a0 must be greater than an. Now, the first three conditions you notice are independent of the Routh or the jury's array, and therefore they can be tested first before formulating the jury's array. And if they stand, we can proceed to determine the jury's array and proceed with the jury stability test. If any of these criteria fails, then the system is unstable and we do not need to proceed to the formulation of the jury's array. Next, once we have the jury's array, number 4 is that the determinant of B0 or the magnitude of B0 must be greater than the magnitude of Bn minus 1. The magnitude of C0 must be greater than the magnitude of Cn minus 2. That means the magnitude of B0, the first term, must be greater than the magnitude of the last term. These terms. The magnitude of C0 must be greater than the magnitude of Cn minus 2, and so on until we have exhausted the terms of the jury's array. And if all those holds, then the system will be said to be stable. If any of them does not stand, then the system is unstable. And that is jury's stability criterion. We first take the polynomial in Z and test for Q of 1 and check that it must be greater than 0. The second test is that negative 1 power n multiplied by Q of negative 1 should be greater than 0. The magnitude of A0 must be less than AN. And number 4, the magnitude of the first term of each array must be greater than the magnitude of the last term in the array. And if all those conditions are met, the system is said to be stable. We can take an example of a system defined by the characteristic equation Q of Z is given by Z cubed minus 1.8 Z squared plus 1.05 Z minus 0.2 is equals to 0. That is the characteristic equation of the system, and we evaluate the stability of the system using the jury's stability test. This is a third order system, and the first criteria is that Q of 1 must be greater than 0. Q of 1 must be greater than 0. That means the terms will be 1 cubed minus 1.8 multiplied by 1 squared plus 1.05 multiplied by 1 minus 0.2. This will give us 0.05, which is greater than 0. The first condition is that Q of 1 must be greater than 0, and our 0.05 is greater than 0, and therefore property number 1 or condition number 1 is met. Condition number 2 is that negative 1 power n multiplied by Q of negative 1 should be greater than 0. Our n is 3, this being a third order system, so negative 1 power 3 multiplied by Q of negative 1. So we'll have this as negative 1 Z cubed, where there is Z we replace with negative 1 minus 1.8 minus, this will be 1.05 times z, z is -1, that gives us 1.05 minus 0.2, negative 0.1 cubed will be negative, the whole of these terms will be negative, and this is 4.05, which is greater than 0, and the second condition is met. Condition number 3 is that our A0 magnitude must be, our A0 magnitude must be less than AN, must be less than AN. That means A0 magnitude must be less than A3, where A3 is 1, the coefficient of Z squared, A2 is negative 1.8, A1 is 1.05, and A0 is negative 0.2. So we can write A0 magnitude is the magnitude of negative 0.2, which we are saying must be less than A3, which is 1. And we notice that 0.2 is less than 1. And condition number 3 is met. And we can now proceed to formulate the jury's array, from which we can proceed with the jury's stability test. When formulating the jury's array, we write our terms as z power 0, power 1, power 2, and power 3. The first two rows will be formulated from the coefficients of our polynomial in z as minus 0.2, 1.05, negative 1.81, and then 1, negative 1.8, 1.05, and negative 0.2. From which our B0, so this is our A0 to A3, A3 to A0. So we expect B0 to B2, and then B2 to B0. Our B0 will be the determinant 0.2 negative, 1, 1, 0.2 negative determinant. So the first two terms and the last two terms formulate our B0, from which the determinant is 0.04 minus 1, which is negative 0.96. And this is minus 0.96. Then our B1 will be formulated using negative 0.2, then 1, 1.8 negative, and 1.05 determinant. So these terms, the first term and the second last terms, to constitute the determinant B1. And if we evaluate these terms, then this is going to be 1.59. This is 1.59. Lastly, we have our B2, which will be the first terms and the second terms to formulate our magnitude, 0.2 negative, 1.05, 1, and negative 1.8 determinant. If we evaluate these, we obtain negative 0.69, and this is minus 0.69. And this is our jury's array. From which we can test the stability of the system by proceeding to check on condition number 4. Now, for condition number 4, we know that the magnitude of B0, must be greater than the magnitude of B2. The magnitude of B0 must be greater than the magnitude of B2. So B0 is negative 0.96 magnitude, which must be greater than the magnitude of B2, which is the magnitude of negative 0.69. And we observe that 0.96 is greater than 0.69, and therefore the fourth condition is met, and the system is said to be stable. Since all the four conditions are met, the system is said to be stable, and that is the jury's stability test as applies to discrete time systems. Otherwise, that is the end of my presentation, and thank you for watching this video.